Okay, let's dive into this. Have you ever been in like a college math class?
Uh-huh. Staring at equations?
Yeah, grappling with differentiation, integration, all that,
Yeah,
and just thinking, is this ever gonna be useful? Like, ever?
totally. You wonder where it applies outside the textbook.
Well, today's deep dive hits exactly that, but maybe in a place you wouldn't expect.
Your kitchen pantry, basically.
Right. We got some source material here, some excerpts.
Yeah, and they explore how those exact math tools are, well, critical for designing the packaging for your food.
Stuff you handle every single day.
Yeah.
Cereal boxes, containers.
Sounds a bit wild, doesn't it? Calculus for designing a milk carton.
It does. But the sources, they lay it out pretty clearly.
And that's kind of our mission here, right? To show you, especially if you're, wading through this stuff in class right now.
How these concepts, which seem so abstract, are actually really concrete.
Uh-huh.
Vital, even.
In the real world, yeah.
Okay, so let's get to the core idea the sources up. They talk a lot about integration.
Right, that whole finding the area under a curve thing, or accumulating quantities.
Exactly, and the sources connect it directly to figuring out the volume inside food packaging.
Makes sense when you think about it. Integration is basically a way to sum up lots of tiny pieces to get a total.
Like adding up infinitesimally small slices of space inside a container.
Precisely. So when engineers design a package, maybe a standard box, maybe something curved like a bottle.
Or even like a bag of chips that kind of puffs out.
Yeah, exactly. They need to know precisely how much it holds. Integration is the tool for calculating that volume accurately, especially for those non-standard shapes.
And why is that precision so crucial? I mean, obviously you want 500 grams of pasta if the box says 500 grams.
That's definitely part of it. Regulations, consumer trust, all that.
But it's more, isn't it? The sources mention efficiency.
Oh, absolutely. Think about wasted space if the packaging is bigger than it needs to be.
That's wasted cardboard or plastic or whatever.
Right, which means higher material costs and higher shipping costs because you fit less on a truck or a shelf.
So getting the volume just right saves money all down the line.
Exactly. Manufacturing relies on that kind of precision. Integration gives them the mathematical power to achieve it. Simple box, length X, width X height, easy.
But most things aren't simple boxes anymore.
No. So integration handles the curves, the weird shapes. It lets designers optimize even for standard shapes, maybe tweak dimensions slightly for max volume with minimum material.
Okay, so integration nails the volume. But you mentioned differentiation earlier. The sources bring that up too. How does that fit in?
Yeah, they often go together, right? Differentiation is about change, finding rates of change, peaks, valleys, finding the optimum.
Like the best possible design.
Sort of. Packaging engineers use it to solve problems. Like, okay, we need this specific volume.
For that 500 gram of pasta.
Right. What dimensions should the box have to use the least amount of cardboard? That's minimizing surface area for a fixed volume. That's a classic optimization problem you solve with differentiation.
Oh, okay. So finding the minimum material needed.
Or how does changing the curve on a bottle just slightly affect how strong it is or how well it stacks on a pallet? Differentiation helps analyze those trade-offs.
So integration tells you how much it holds.
And differentiation helps figure out the best way to hold it, considering costs, materials, maybe even how it feels in your hand.
Wow, so they really work together, these two big calculus concepts.
Like two sides of the same coin, yeah. One confirms what the volume, the other optimizes how the shape and dimensions based on all those factors the sources talk about.
So for you listening, maybe struggling with those integrals or derivatives,
That math you're learning, it's not just theory.
it's being used right now by people designing the physical world around you, making sure your food gets to you efficiently, safely.
And accurately measured. It impacts costs, logistics, sustainability. It's pretty fundamental stuff.
It really connects the classroom to, well, the breakfast table.
It really does, and it makes you think.
Yeah, like, what else is out there? Consider this. What other mathematical ideas, maybe ones that seem even more abstract right now?
Might be quietly shaping the world around us in ways we haven't even noticed yet.
Something to think about.
Yeah.
You might start seeing math hiding in plain sight.